I'm just checking that we have everyone. So Carlo is there, Roberto, and the third speaker is... No, the third. No, Roberto is the first, and then we have Carlo and Vaira, yeah. Yeah, it's just... okay, I will...
Yeah, thank you.
Okay.
You don't need to click everything.
Okay, so I will just do a quick introduction. So this session is about the facility definition team. So this is an exercise that was started to prepare for the post-ISS in low Earth orbit. And so for today, we have 3 presentations that are tackling 3 topics, 3 fields. So one is the soft matter and biophysics, another one on fluid physics, and the last one will be on material science. And there will be another session on FDT, more on fundamental physics, tackling cold atom and atomic clock, and that will be at the last sessions on the last day and in the afternoon. But I encourage you also to assist to this one. The first presentation will be by Roberto Ciabino, and maybe I'll leave the floor to you. Thanks.
Thanks so much, Sebastian. Good afternoon, everyone. After a short break, we are still here. So today I'm going to tell you a little bit about what we have been doing in this soft matter and biophysics facility definition team. And since I was the first speaker, I decided I also try to give a definition of facility definition team that I found on the ESA website, because the first time I heard this term, I didn't even know what they were talking about. And a facility definition team is a group of people organized by ESA that should design and conceptualize advanced research facilities for space missions. And the concept that is put forward, at least in this declaratory, is that of a concurrent engineering methodology to ensure interdisciplinary collaboration from the outset and streamlining design process and improving facility integration for scientific and technological advancements. So if you are like me, this is just a mumble thing. So my personal definition is a think tank of people from different disciplines with a task to identify and describe new research facilities plus associated scientific objectives. And in particular, we got interested in this because SciSpace published a call with a deadline that was extended October 8, 2023. So this is a pretty fresh initiative. And the idea is that they wanted to have some SciSpace FDTs to support upcoming science requirement, definition, feasibility, and development studies with a focus on low Earth orbit. So the focus of this was specifically and it was also clear from the title, for the post-ISS era. This was the title of the call. Now, and the tasks that were identified in this call as a possible request from ESA to these teams was to identify and constrain prioritized science exploration objectives, to support the definition of scientific requirements related to those objectives, to assess and advise the scientific impact of these requirements, to assist in identifying or making the trade-offs that are needed between the facility performance and the objectives, and last but not least, assess also the feasibility of a mission or facility concept to deliver on the science objective defined. To do that, we didn't have so much time because this was the call, and the end of work is supposed to be before the end of this year. And these are a lot of objectives. So I will show you what we have been doing so far in the specific case of soft matter and biophysics. So if you open the call, you will find a document like this, where it explains to you what soft matter is. I don't need to do it. But the last 3 lines are particularly interesting. This was the specific task for this facility definition team. Will provide consultation and support for the definition of capabilities and key scientific requirements necessary to achieve the desired capabilities for future facilities addressing these topics. And a very important point is that 2 lines before, there was this piece of text that told us that we had to start not from scratch, but from the white paper that was recently updated in 2021 on soft matter and biophysics with the most fundamental questions for the future. Now, this is the document, this is the white paper I'm talking about. And you see, there are many contributors. Some of them are here, Alberto and Matthias. Yeah, I was looking for you, but I didn't find you. And some others are not here, but these people wrote down what the interesting topics, according to them, were in this field. And the outcome of this document was to list 7 different topics that were deemed as critical for the future of soft matter and biophysics research in space. Now, with this in mind, the team was formed by ESA, and the team is comprised of all these nice people. And by looking at this picture, we learn a lot of things. For instance, that people like Annina and Andre, maybe they have to put more recent pictures online because they are not very much updated. We learned that we don't have so many women. We have Laura, we have Christina, we have Olfa, we have Annina, but we also have Thomas with long hair that maybe qualify as a woman in a way. But we did our best, and I mean, we're happy that they were in the team because they brought a lot of know-how. And also, I kind of understood why the first flag here is Germany, because there is this very strange ordering of flags. I don't know if you noticed that, because they are almost alphabetical: Austria, Belgium. Yeah? In French. Okay. Okay, interesting. I discover something new every day. But the alternative explanation is that there were a lot of German people in our team, so they are 7, and then followed by 4 French members, even though Olfa is transitioning from Germany to France, so she will soon have a French flag. And then there is a representation from Italy, Luigi, Gigi, Alberto, and then there is a representation from Austria, which is me. And we were coordinated by 2 pillars of the ESA, Pepe and Marco. Pepe in the initial phase and Marco in the final phase. And with this beautiful team of people who are all smiling, I don't know if you noticed, but everyone is smiling in this picture. So this means that it was a very nice team to work with. We started working. And so the starting point, as I told you, was the soft matter paper. So the way we organized our work was monthly online meetings, starting with the first meeting on November 20. Sorry, this is wrong, of course, it's November 23, not November 24, because we cannot go in the future. Then we had offline work by all the team members, plus some one-to-one meetings between the scientific coordinator and the ESA coordinator. And we had a 1 in-person meeting in Vienna in July 2024, a 2-day meeting with a critical analysis of the output document draft, which is the main document that we will deliver to ESA as a result of our work. Plus, we organized some team-based activities by dividing people in subgroups related to topics. We assigned them questions. And at the end of the event, we had a vague idea of possible superposition between the different topics. So we decided to work again offline, and then today in the afternoon, after this session and tomorrow, we will aim to finalize the document to be sent to ESA before the end of the year, which is this. Now, what are the research domains that we identified after all this work as the ones that we think would be more important to pursue in the future? Well, the first one is diffusion processes. Diffusion processes with the idea that as a potential delivery, I swear that I didn't modify the presentation after your question today. This was already like that. With a potential consequence on how we handle fluids, delivery drugs, and what are the potential consequences for diffusion in biological systems. Granular material to explore flow, cohesion, and stability to optimize resource utilization and infrastructure development in extraterrestrial settings. Matthias made a good example of concrete, for instance, today. Nano to micron scale soft objects, so basically soft material elementary building blocks to create durable and adaptable materials for space applications. Dust in low density plasmas to analyze cosmic dust behavior to mitigate spacecraft risk and advanced planetary science, and biological and synthetic soft systems to study the adaptation and synthetic material behavior in low gravity to support astronaut health and health support technology. Now, what you see there is not what we think we can do in a couple of years, right? So we will never be able to reach these goals in such a short time. But this is where we see that all these fields of research can go in the future. So where do we, if you want, these are our dreams. What will make us happy to make a contribution in these 5 areas on those critical, let's say, issues. And in addition to these key areas, we have identified 4 strategic objectives that in our vision mirror the interdisciplinary nature of soft matter, because all of them are quite diverse. The first one is, of course, the basic one. While we do science to advance fundamental understanding of soft matter in low gravity. And the second one is to develop materials and systems that are optimized for space exploration. This is something that we have very clear in mind, that if these things are going to be useful, this needs to be there. They need to be useful also for space exploration. Resilient, radiation-resilient materials, and so on and so on. The third one is to enable a sustainable use of extraterrestrial resources, and in particular, how do we think we're going to establish a long-term human presence in space? This is not a question that we will be able to answer here, but we hope to be able to make significant contributions with our experiments and the facilities. And the last one, enhance biophysical research for health and sustainability. This connects back to something that we also discussed earlier in the last session of the day. We hope to make progress in understanding the behavior of biophysical systems in microgravity, because we know that if we do, this will have implication for the health of astronauts in first, but also of future, let's say, I don't like to call it colony, I know this term is controversial, but let's say future presence of humans in space. Now, for each one of the 5 objectives, of the 5 domains that I showed you in the previous slides, 2 slides ago, we also identified some more focused short time objectives that are the ones that we think we are going to be able to address, and they are all more fundamental than the longer term vision. And these ones are actually things that we can do tomorrow. So this is what we will do if we can really fly this facility. And the first one is the confinement of fluctuations during diffusion processes, which goes back to the diffusion key area. The second one is aging dynamics of granular particle beds. The third one is behavior of nano to micron scale soft objects in terms of assembly, stability, and resilience to external manipulation. For instance, mechanical or acoustical manipulation or magnetic manipulation. The fourth one is dynamics of dust particles in low-density plasmas. And the fifth one is the adaptation of non-living and living soft matter systems. In particular, how the structural, the mechanical, and organizational properties of these real living materials or biomimetic ones that are not living but are engineered to reproduce the properties of the living ones will behave under low gravity conditions. So the next step was also to do a critical analysis of the past experiences of every member of the team. And this was a very long exercise we did at the beginning, integrated also by some more recent things that we did with Marco in preparation for this presentation. And we started from 4 experiments that have been conducted in the past, some of them still running, like soft matter dynamics, and where we can count things. And what we decided to count? Well, we decided to count, first of all, the number of key areas in which this gave a contribution. And there is a substantial overlap of these experiments with many of the key areas I showed you, which means that we're not coming out with something which is completely new. We are coming out with something which will give new information about problems that are interesting since a long time. It's not that diffusion became interesting today. Diffusion has always been interesting because we know that it's at the basis of many fundamental processes in materials production and in nature. And also, in addition, we counted publications, number of missions, and development in years from the announcement of opportunity to launch. And this is a very interesting exercise because there is a lot of variability. So, of course, we can read these numbers in many different ways. The way I want to read them with you today is this, which is that multi-experimental facilities require very long development times. Then they give a good output, but they require many, many years. Are we really sure we want to wait 18 years? This was also in the discussion today, to get 9 papers. Maybe yes, maybe no. This is a question that we have to ask very honestly ourselves when we imagine the future of the facility. On the other hand, shorter development times do not seem to compromise the quality of achieved results. So if you see here, for instance, 8 and 9 years of development time, we had 5 and 10 publications. So this means that we can get good scientific output also if the development time is not that long. So of course, we could spend, I think, 30 minutes only by trying to read and interpret these results, but I will move forward. I will move forward with another set of considerations that came from the team members this time. The first one was that we need to do something that lowers the entry barrier to space research. Alberto said today, I'm here 20 years, I see always the same faces. Well, this is not nice. We want to see new faces, right? How do we get new faces here? Well, we get new faces if we lower the barrier and we convince people that this is something that they want to do, and this is something that they can do. This is not that complicated. Now, convincing people that this is not that complicated, if you ask access to data that have been acquired in a space experiment, and you don't even know how to open them because they are in a proprietary format, and the reader is not included in the data, well, that's not the best start, I would say. Can we do better? We think that we can do. Of course, based also on what we saw earlier, we strongly believe that decreasing the development times must be done. So we need to better align with academic timelines. The duration of a PhD student thesis, 3-4 years, maybe of a couple of them if we really want to make things gradually, but we cannot wait 20 years for an experiment. We need to add robustness and flexibility to our facilities. So a facility that does only one thing maybe is not a good investment. Stefano today in the session said, what do we need to do submatter research in normal gravity conditions? We need light scattering, microscopy, and a rheometer. With these 3 instruments, we do 96% of our experiments. Why don't we do the same there? Why don't we have a soft matter lab that is modular and flexible and so on and so on? And so this brings me to the final point, which is maybe we can still keep the concept of a single-use facility that maybe is more complicated and maybe more focused. But beside this, we may want to have also another concept, the one of smaller, modular, and possibly scalable setups that maybe start small and become larger and more complex when you need them to be. So our dream here, because maybe you fall asleep at some point and this can get lost in a sea of words, our dream would be that of an IKEA-like software that scientists use when they want to design a setup, and they choose a light source, and then many of the building blocks disappear because they are not compatible with that light source. So the scientist doesn't need to know what is compatible, needs to know what they want to do, and needs to be able to design part of their experiment, at least conceptually, by themselves. Then it's the work of the engineers to convert this thing into a real instrument. But if we design it in such a way that from the very beginning is thought and conceived in a way that makes this possible, well, this, in our view, will solve many of the criticalities that we mentioned earlier. So our primary goal then became to start to think about a state-of-the-art modular facility to do research in microgravity with, of course, the 2 main objectives: to investigate phenomena that are unique to space, because without that there is no sense. And second, also to act on both levels, at the level of the fundamental understanding, but also with in mind always the fundamental applications that may come after 10 years. Those, yes, they come after 10 years, but not the experiment. The applications of the results, because we know this is the typical time also on Earth. It's not that you discover something. So the laser is a classical example, was discovered in the 60s, and then it was really commercialized in the 90s or in the 80s, I would say, maybe in the 90s. So this modular design will be, in our view, a solution to many of the challenges, will ensure adaptability, accessibility, and also the possibility of reusing this instrumentation for a diverse set of experiments. Because if we have a good microscopy modular setup, this is not only useful for soft matter people, this is also useful for biophysics people, which are in this group, but also for biology people who are not in this group. And maybe they may add another building block that we have not thought about, even though we have thought about some that can also be useful for biological experiments and so on and so on. And if we do that, then this would really lower the barriers, which is one of the things that we identified earlier. But in addition, as an added bonus, will also probably help facilitating interdisciplinary research, like the communication between physics and biology we were discussing earlier, because if we share the same instrumentation, then we can all try to optimize our efforts toward the goal. Now, this is a very schematic, this is not even final, but I just wanted to put it there to give you an idea. The idea is that we have a very modular system where people can choose different, so each one of these things is not a choice, is a building block which is representative of a possible category. For instance, this could be laser, so the user could choose that this is a laser or an LED or a superluminous diode, and then the user can also choose to have a detector that is a camera for high resolution but not speed, a camera with speed and no resolution, and so on and so on. So the idea is to try to disentangle and decouple all the building blocks and to make it a little bit more user-friendly in the design phase. So imagine that you want to build an instrument, then in our view, somebody will click here and choose the illumination, and when they chose laser, some of these things will show options that are more limited, because with the laser, you lose some opportunities and you gain some other opportunities, okay? And so on and so on. So the flexible facility concept is, if you want, also enriched by the fact that we don't know, at least we don't know, maybe you guys know, but we don't know where we're going. So post-ISS era, for us, is the sea of darkness. So we don't know if we are going to fly on a new space station, if we're going to fly on small rockets like photon or vectors like photons. We don't know these things. So since we don't know, we have to imagine a concept which is ready also for everything. And this, in our view, would be to ensure that the modularity is also scalable, flexible and scalable, in such a way that we can start from the simple design, which is the one of a free flyer platform, like a single locker. Then this is the basic unit of our modularity. And then if we want something which is more complex, we go to a double locker that may be also hosted in a commercial space station module into the future, who knows. And then if we really want to do a step forward, we think of something which is more similar to what we do today. So a sort of post-ISS facility. So to do that, we needed to do an exercise which is still not finished. We're going to finish it in these 2 days. But for each of the key research domains and the associated scientific objectives, we had to ask a question: what do we really need? What makes it optimal? And what makes it very advanced? And based on this categorization, we divided the features of the setup in 3 categories. One are the essential features. The second one are the optimal features. And the third one are advanced features. Now, I know this may sound very abstract. That's why I reported here one of the examples with all the different categorization. The example is the first scientific objective that I mentioned, which is confinement of fluctuations during diffusion processes. For this, we had this objective, which is to investigate interactions between macromolecules or microparticles in solution in the presence of temperature or concentration gradients. The samples are colloidal particles, proteins, and macromolecules. The diagnostic is divided. The diagnostic here is intended as illumination plus detection. Is divided in essential. What would we deem as essential? Well, multimodal imaging with different imaging contrast mode, bright field, phase contrast, dark field, shadowgraphy, and so on and so on. What do we deem as optimal? Well, if we want something that will really make this setup optimal, well, we need to have wide field fluorescence, confocal and light sheet. What will make it advanced? Well, optical tweezers and total internal reflection microscopy. Okay? Then we do the same thing for the manipulation. What are the essential elements? Well, thermal control, microfluidics, what are optimal, temperature gradients, centrifuge light patterns, what are advanced FRAP for dynamic study of diffusion processes. And now we are still doing this exercise for all the 5 scientific objectives and scientific areas. And at the end of this, we will prepare a matrix telling us what are the essential features that are shared by all this research. And then we will make a decision, okay, maybe we can do everything with 1 facility, maybe we need to have 2 facilities with different features, different scale, and so on and so on. So if you want to know more, you have to remain tuned, because we are not finished with our activity. And thank you very much for your attention, and I'm ready to take questions.
Thank you very much. So normally, if we want to stick to the time, it should be, we have probably time for 5 minutes questions. But thanks again for your presentation, very clear. Do we have any questions in the audience? If we need so, we can use the microphone.
Okay, just a curiosity, because it doesn't know if you have a sort of ISS or something different. The crew time is something that in principle should not be there, because maybe it's simply an instrument that should be built on Earth and fly, or you imagine a way to change the thing on space?
No, I mean, the way we are thinking now is, if we go to the space station, maybe you can also think, but the way we're thinking now is something modular. So the idea is that we don't care what happens next. This we don't know. The instrument can be destroyed or brought back for reconfiguration, whatever. But the idea is that engineers will do the initial effort at the beginning of the project, where they devise all the possible building blocks. And then whenever we want to reconfigure this, the engineering effort will be virtually 0. We'll basically a performance test, and that's it. So the modularity concept is bringing the challenge at the beginning of the development, because you need to conceive modules that are compatible with each other. And then maybe at the end of this exercise, we'll discover that some of our features will be gone, because in our dreams they were compatible, but then in practice they are not. But then when you have it, the user will not need to take care too much about how to make this happen. They just need to know that this can happen. If they want to study a cell monolayer with phase contrast and confocal, they don't need to care too much. They just select the building blocks that they want, and the rest will be done by the engineering people.
Do we have other questions? Otherwise, I can also ask. Maybe I can start with, and there will be room also for. So thanks for this concept, and I understand also that this concept is with the idea to have maybe a more flexible and fast also turnover of experiment. And then you had a slide also that shows how long it is in some cases to develop. In your idea, would the idea to develop this first instrument faster also, or the idea is to develop maybe the idea is that you develop the instrument, and then the turnover, once you have built it, you can refly it several times?
So this could be developed faster and basically replicated like I don't want to mention any country, like a sort of factory, where people just follow instructions and they build it. So
the classical one is the same industry that are used currently to develop the
this could be not. So the idea is that we don't know who is going to do it. This is your job. Yeah. What we know is what we want, or what we think could be beneficial for research in space. And we think that this concept could be beneficial because the idea, in the lab, these things exist. So if you Google, or I can send you links, you can find modular microscopy experiments where you can really configure with blocks your microscope. And this is something that you can 3D print yourself at home. And okay, I don't want to imply that we have to 3D print at home our flight experiments. Maybe we can make it more professionally. But if this can be also made open source, like Alberto said, open access, open source, then people can, including scientists, could replicate this setup on ground. And they can reproduce the same kind of experiments on ground while they are in space. So the business model must change for this. Yeah. It's completely different from the one we're used to. But we see a possibility that everyone could be happy.
Because if I may, just another question also was related to the community you are addressing. So in physics, very often the scientists are building their own experiments, so they have a good competency on the optics, all the techniques that they use in diagnostic. Whereas for biology, that you mentioned also as a cross field, it is less the case. Very often the scientists are building something that is more commercially available, more standardized, and so how will you see these interactions?
I think this will make both happy, because the instrument will be developed for maybe initially for our type of research, but when the concept is available, then everyone will be literally able to design an experiment. They don't need to do an effort to imagine what is compatible with space, because this was done a priori. Okay. So in this, let's say, phase space of all the possibilities, you will list all the possible configurations, and those that are not possible, the scientists will know it from the very beginning. So I want to do this with that. No, this is not possible.
We have time for another question. Yeah, thank you.
Very interesting. I would like to know, how do you come up with these catalogs or these modules? It's based on the past experience, or you want to build all the possible? Yes.
This page is based on past experience. So we know that there are these three types. I mean, this commercial space station is not a past experience. Is what has been discussed will be the future of
to the components.
The components.
Yes.
Yeah.
So you say different.
So this slide.
Yes, yes.
Yeah, we came out by analyzing all the setups that we use in the labs, all the setups that we used in the past in space experiments, and how we could decompose the different building blocks. This is not final, right? So this is still, we're working on this. We want to make it even simpler.
Yes,
but,
because in space only restricted number of cameras and restricted number of laser setup has gone. So we have only experience based on that restricted number. So in order to have multiple choice, how will you say that it will still work on space platforms?
Well, if you remove humans, already you get a lot of flexibility. So if there is no astronaut there, you can already choose many more cameras, many more lasers. If this thing goes on a free flyer, I guess, correct me if I'm wrong, maybe only if you put a bomb on it, you cannot fly it. But the rest, I think, is pretty fine. So you don't need to do, don't have the same level of restrictions that you have in the type of experiments that you may be used to in ISS, where you cannot bring your own solvent if it is not approved by NASA, and so on and so on and so on.
Okay.
Yes. Yes, I mean, of course, if you want to fly a biological virus, pathogenic for man, for human, maybe even with a free flyer is not such a nice idea. But if it is something that does not represent any risk.
Yeah, but then the automation becomes more complicated in such cases.
Yeah, but I mean, the photon experiment that you saw was a double locker with 2 experiments on top. It was completely automated with telecommand. No astronaut, nothing. And this was flying for 26 days, together with other 20 experiments in the same box. Everything worked perfectly. We had to fight for resources with the other experiments because the people willing to film the fishes were using a lot of power, and when they were doing this, we could not acquire the images. But apart from that, I mean, of course, there are challenges, energy and so on and so on. But the degree of complexity is way lower than ISS in this type of things.
Okay, thank you.
Thank you.
Thank you very much, and maybe we can, thanks again, Roberto. And we have our next speaker, so it is another facility definition team, looking more at the fluid physics, and Carlo, floor is yours.
Is this? Maybe it's the wrong one.
Yeah, so...
Sorry. If you want, I can speak also, but it's not mine.
Yeah.
And I am already sorry because I know that I have not respected the wonderful template provided, but just because it was done a bit in a situation not so easy for traveling around. Hello? Is there anybody out there?
Yeah, you are here.
That is not this one? Okay, in any case, let me first
Maybe you can
thanks
introduce
Roberto,
yeah.
because Roberto basically, okay, that's it. Okay, that's it. To thank Roberto, because actually my presentation is rather short, and I missed also, and this was very interesting, that Roberto basically summarized all the process that in this facility team we have endured. So in terms of meeting, in terms of prioritization, in terms of searching for what can be a solution. And me, I have coordinated in the sense that, of course, this, okay, yes, the group together with a lot of friends and colleagues, and as you can see, the contributors to the facility definition teams for fluid physics comes from a different country, a bit both European and extra-European, and from a different also background. And this is for a reason also we have been followed and coordinated by Sebastian is here, Giuseppe Correale and Balash, that I think that I have not seen him, so possibly could not come, and lately from Marco in the last few months. And so actually my presentation is rather short, because it follows the same schemes that Roberto was presenting. So the first goal was to try to consider some key scientific challenges that are open and objective in fluid physics, and focusing on some mechanism that has been studied in the past, but also by enlarging this kind of studies to new challenges that allow and enable the future. And also, as was suggested before, to try to figure out what kind of facility infrastructure could allow to fulfill this kind of scientific objectives. Now, what I think that is very important is also to understand why fluid physics in space, because we have to consider that the facility and also the logic for the new facilities, or also the way we address the challenges, is basically because we are very close to the surface of the Earth for the moment with our outpost, the ISS. And the science that we are producing by exploiting microgravity is on one side enabled by the special environmental condition of space. So, for example, by going back to Earth, the phenomenon for the people that were on the breakout session 1 this morning, there are a lot of experiments that in fluid physics that have been presented and have been or already done or will be done in the next years on board the International Space Station. But at the end of the day, the experiments that are that have been done on the ISS and on the ground-based platform have enabled not only the possibility for going further in space exploration, but have allowed to refine, for example, numerical model or physical model of phenomenon that can be used also for Earth application. So that's why we like the concept of a facility that will enable science, and by enabling science will look back at the Earth, but also will position its results in terms of the future of space exploration. You know, I think that there is a lot of hypes, maybe pushed by the recent success of big commercial companies and bigger players like, for example, SpaceX of Elon Musk, in considering that we are going to the moon and then on Mars and then whatever, we will create colonies, cities, and so on and so forth. But each time, so 2 days ago, yesterday, I was in Dubai to present why material science is important for space. And one of the questions that they asked me continuously each time that I go presenting the future of space exploration is, but okay, Carlo, everything is very nice, you are producing results and this, and this, and why after 55, I was born the years of the landing on of Apollo, after all this year, we are really basically in terms stuck not so far. So we are speaking about creating outposts here on Mars in the future in 4 years, 8 years. But the question is why we are here. So there are several reasons. One for sure has been, especially in the past, the end of the Cold War. You know, at the beginning there was a fight, and so this promoted a lot. Also, there are economical reasons. You go farther, it costs much more. But the real truth is also that we really lack the entire toolbox of enabling knowledge and enable knowledge that will allow to create outputs. So looking at the presentation of Roberto, fluid physics has a lot of point of contact with the soft matter and biophysics, to the point that, for example, in fluid physics, we are studying also biological fluids like blood and so on and so forth. But all of this you find as an enabling technology to be further. So if we do not enable knowing what we have identified, at least for the fluid physics, as our priorities, that it looks a bit dry saying heat and mass transfer for single and multi-component, but at the end of the day, it will be what this knowledge will enable major energy efficiency systems on Earth. For example, a lot of these mechanisms of phase change have been in the Emirates, and they are using some of the results for a better desalination plant. So, I mean, if we enable this science, and unless we enable this science, we cannot go back to the Earth, but also we cannot really hope that we will have a sustainable future space exploration. Because for this, for dust mitigation, there are systems that implies, we can say procedure that implies also, for example, spray or condensation on surfaces. And for life support system, you would need for sure to manage the full closed loop in terms of water, humidity, thermal control. So basically, speaking, just saying, oh, we will go to the moon and then we will go to Mars, without first understand what are the basic principles, translating this basic principle in something that is engineering valuable for developing this, we can say, enabling technology, is, if you want my personal opinion, just an hype, in the sense that it's good because it push the stuff, but it will not be so easy to go there. I guess that later the material science will speak about the protection from radiation. So this was, just to tell you, this was the baseline. We have to enable science in order to come back to Earth, that is always a good stuff, to save also our planet through better modeling and so on, and also by understanding this kind of phenomena to enable what are points that could not be overlooked if we really, practically, we want to create a multi-planetary species, as is always said. So, what our community has done. As someone knows, the community of fluid physics is one of the biggest. I think that in the topical team of heat and mass transfer that is coordinated by Professor Di Marco of the University of Pisa, I don't know, maybe you are more than 30 or 35 different groups. So it means, as also has been described today by Sentil, by Andrei, by Axel, basically we have used so far all the possible facilities that are provided thanks to the support of ESA. And I tried to check on the Erasmus archives. I think that it has been generated more than 200 campaigns of all of this. Of course, a few on the ISS, but sounding rocket, parabolic flight, drop tower, and centrifuge has been actually, CREST has also used the capsule like the Photon that now is not active. I don't know if it's active. I don't think that it's active anymore. But so we have studied drop and bubble dynamics, boiling, for example, access. It was with Tatiana Verim and Catherine Collin involved on Ruby. And then we have the effects of fields, like the electric fields Sentil explained for the droplet, the drop experiments, and then the condensation on fins, for example. Evaporation and condensation allow for closed loop, just to explain to everybody. And then we have a flow boiling, the liquid, acoustofluidics, there was Ricard here, the self-rewetting fluids that are very similar to the possibility to have, you know, a better thermal structure. So basically we have done a lot. I have counted just in the last 10 years the publication related to this platform, and I think that we are on around 200, 250. Of course, we are also a lot of groups involved. And what we learned. So by putting together, I don't want to be negative in the sense that both parabolic flights and the experiments that we have done so far, I want to say that generally speaking, of course it's not a quantitative metric, but generally speaking we obtained what we were looking for. It's undoubtable that are not just simply experiments that will be done and we don't have data. Most of the data have been published by considering the microgravity data for modeling. So if also looking at our discussion, the experiments in microgravity, thanks to this platform, were relatively effective and we are happy. And also, despite we were a big group, we had a lot of partnering possibility, and so different consortia has been built by having not all the partners together. So this, with more than 30 participants, has multiplied the number of consortium and so of experiments, and we generated a lot of valuable data that were at the basis of this big number of publication. Also, we used this data in order to refine modeling that were started. You know, like, I don't want to say, but sometimes you have to start with like some sort of serendip solution and then go on. So this will be, this was one of the first outcome. And we have to say that we had a lot of spin-off to other projects, thanks to the fluid physics studies, so the studies about phase change and so on. So, for example, there are people that are now working on greenhouses and so on, close the loop for bioregeneration. So there are spin-off from the project that we have learned. But as usual, we have also some dark side. And this was spotted also by Roberto, and I think that is very common for the community that is in this domain. There is a lot of time that we should wait, especially for important platforms, so long duration platform like the ISS, between the moment an experiment is really conceived to the moment where you can implement the experiments, to the point that sometimes part of the community has disappeared. You know, it's life. Someone retired, someone dies, and so on. And we have The fluid physics community has really experienced that, because our experiments sometimes are waiting. You have the maximum of 18 years, we have 22. So, so it means that it's really long. And I think that this is the biggest dark side. Then we have, you know, some problems. I should say that lately there are many efforts to reduce this gap between the academic and scientific, we can say, players, and then the development in terms of industrial payload. So this has been one of the sides that in this moment have also created sometimes a bit of tendency to the community to get out of the science on space science domain. Because essentially, and this is, sorry if I am a bit harsh on this, many times there are, of course, engineering reasons, but many times the scientists are spending maybe even 1 year of time to create requirements and to understand and to create some sort of ideal breadboard and so on. And then we see these requirements cut in half, in 25%, and so on and so forth. And I think that for whatever is the solution of the next infrastructure, I don't know if it's really one facility, more facility, but these gaps should be fulfilled. And in our discussion, I would like, okay, just before I don't want to lose too much time, these are the different topics that we have prioritized for the moment and that summarize what we don't know yet, always to get back in order to have an enabled science by the space environment that will allow them to go on. What we need to go beyond. So the discussion is open. I summarize saying that we would need one facility and to try to recreate 3 different environments. Only because when discussing internally in the facility definition teams, we chose basically to categorize the open point or based on the kind of a typical size scale, like for example, micrometric, centimetric scale, or nanometric scale in terms of the typical length of the phenomena, or to consider specific environment, like for example, cryogenic. You know, cryogenic refers to a bunch of phenomena that are the same or similar to what you can study at higher temperature, but of course in a completely different range. So it's not so easy to then create a matching between the different modules. But at the end of the day, we need to recreate 3 environments to fulfill the full bunch of topics that we don't know yet. And we get down to the same concept that Roberto was explaining. So to create, we have a lot of common diagnostic, we have the possibility to create a high modularity, and especially insist on the COTS approach. This is very important. A lot of our facilities are also complex because we are basically rediscovering and recreating things that can be easily bought commercially. And then, of course, if you have modules, you have specific instrumentation, dedicated electronics, and special handling. Now, just to wrap up and to say that in our case, when we discussed, the conclusion that we had is similar, but not completely so deterministic as, for example, in the presentation of Roberto, because the modularity is easy to declare, is very difficult, at least in the case of our topic, to implement. It requires an effort that maybe is not worthy in terms of trade-off. So the question is open. Of course, we consider this, as Sebastian was saying, as an exercise. It's not like the final stamps on what we want to do for the future. But up to now, facilities that can do many things at a time, for sure have their own rationale, but it's not said that is the best one that we can look for. Especially in item mass transfer, there are complexities and we can say size of the payloads in order to allow for heat exchange and so on that cannot be easily put in common with any other experiments. So the idea is that maybe one facility can be able to cover all the environments that we need with a modular concept. In practice, we don't have yet a definite solution that this can be done. So we have also to be open-minded to different approach or to different concept in terms of infrastructure. So with this, I have finished. This is some sort of Hall effects model.
Thank you very much.
Thank you.
We have time for a few questions, actually. So is there any? Oh, you have?
I'm the first. Thank you. Nice presentation. I want just to underline that the importance of the liquid, the liquid and droplet interaction, which is a subject also of the other facility team that Roberto was summarizing.
Exactly.
And as a matter of fact, there is an idea of the boiling emulsions as a means of cooling.
Exactly.
Yeah, there was this exercise that we did together with Theodoros Karapantsios, the group in Thessaloniki, and the group of Naples.
By the way,
Theodoros
is also part of this.
So we were trying to. So there's probably space for common science. I mean, fluid and immiscible fluids are similar.
Yes, this
so
for sure.
To underline that, yeah, probably something could come out
This
which is good for both.
This is another of the questions that I think should be really discussed. So, for example, as you know, we are doing also colloid, and for example, CREST has done not one, not two, but 4 experiments on diffusion. And even mixing and multi-component diffusion that in some way is at the frontiers between the two domains. The point really that we cannot solve immediately is how we can get to this hoped for modularity, because it's not so easy then because at the end of the day, what we fear is, especially because we have this kind of a huge number of topics spanning up and down. Maybe in biology, it's easier to do some kind of categorization. In our case, basically, modular can mean also automatically select some kind of physics or fluid physics and eliminate some other kind of fluid physics. So this is the open question that I think, I don't know if my colleagues agree, we have not to get down to pin as a final, answer.
Thanks. And we have Santiago.
Carlo, I can ask you later, but I wanted everyone to know, is it okay that the engineering team get involved even in the ESR stage?
So
Because,
I know that
the feedback from them and feedback from us is the one going front and back. If that could be already addressed during the preparation of the ESR, that this is what we can.
So my personal opinion is that, but now I don't want to create, my personal opinion is really that one of the critical point and sometimes bottleneck in the decision is that at the beginning, when the science is proposing an idea, basically is taken out from the scientist to the industrial partner, and it's not their fault that they should just have the hit on them and say, oh, what this fucking scientist is trying to say, he wants a pump, he wants stuff like this. So it's very good if at the beginning we can interact immediately, or even to suggest some sort of breadboard configuration, and so maybe start from there. But of course there is also ESA that is the mastermind and choose the way that is also, you know, acceptable for the, I mean.
But just quickly on the diagnostic, and do you have in mind some diagnostic that needs,
we have a selection in the document, and now it was too long.
But maybe some diagnostic that you feel, for example, they are too bulky, they need to be reduced, or they need to be...
This we have in the document. I didn't report, but we have a diagnostic that can really be reduced, but also substituted once and for all by COTS, you know, because now we have, for example, cameras that, even commercial cameras that can do more, are even more than necessary, and a lot can be shrinked down in terms also of packaging of the full system.
Any last questions? Maybe I will ask just a last one. For example, for the development, I think it was mentioned also in the previous presentation and so on. Where do you think the scientists should sit in the development? Should they be involved? Should, for example, we should leave the scientists also to develop themselves part of this?
Now, this is my personal opinion. So my personal opinion is that really, at least from my experience, at the beginning of the definition between what a scientist has been approved, we can say, by the peer review at ESA. So they propose an idea and they say, okay, I want to do this, and the breadboard part, I think that scientists should really be in. Then I don't think that is critical later, because, for example, we, even for, in general, an academic institution or a research center, is very difficult then to deal with the more industrial part. It means packaging, safety, certification, and so on. So this part will, in my opinion, will stay always in the realm of industry, because they are the only one that can deal with it. For example, we cannot really assure for a safety or a certification. Even if we have the knowledge, we cannot do this. But the first part is really critical, because industry, what we have experienced, I think everybody, is really struggling to understand what the scientist wants. And so often we receive a design or something that is already too late to modify. So if we intercept this part of the process, I guess that we can reduce time and maybe even budget and whatsoever for reason.
Thanks very much, and maybe we can thank again Carlo for this presentation. And we will have the next presentation on the facility definition team on the material science. Maybe you can give the floor to that. Let's check that the presentation is...
Yes. For the sorry.
there is a special
Now this is
announcement,
some sort of announcement for the dinner.
No.
Yes, the FDT meeting, yes. Yeah. So the FDT meeting, the dinner. No, because it was before the dinner. So the FDT in fluid physics, we will have a meeting this evening before the dinner. That's it. Where I don't remember. I thought that we are already decided. So, okay, so sorry, Giuseppe had the right version. I was completely confused. Thanks again. You have another one. This is yours.
You can start. So now we have the... Maybe So this is the last presentation we have on these sessions on the facility definition team. This is on material science, and Vajera will do the presentation on behalf of the science team. And the floor is yours, please.
Thank you. Okay, my name is Vajra Merihanage. I'm from University of Manchester. So I'm presenting on behalf of Material Science Facility Definition team. So here are our members put on alphabetical order. And we miss our ESA coordinator or member of the team. So this is about material. If I go to the our facility definition teams, I would say we can say our basic goal is to advise on the next generation of material research facilities for post-ISS, lower Earth orbit platforms on behalf of the concerned scientific community. If I would say, even though we say material science, our case, we are more focused on solidification. So to define the next generation facilities, first what we were looking at, our previous material science facilities, or with say heritage. So we can try to understand what we had for the movement over last 20 years. So we had basically 4 main facilities were used by scientists. So this includes material science laboratory, electromagnetic levitator, transparent alloys apparatus, and X-ray facility. So some of the facilities has been used more than one platform. So for example, material science laboratory is mainly used in ISS, but something like transparent alloys over different platforms, and X-ray facility to be still to be planned on ISS. So these material science experiments were based on different facilities, and we just tried to understand initially what we learned from these individual facilities. So I would initially give you some wrap up about what we have and what we learn. So first, if I go to the material science laboratory, which is on board ISS on Material Science Research Rack. So it's basically, I think in this morning, presentations give a lot more information about these facilities, but I just try to give a 1 minute idea about. So this basically, I would say, is a Bridgman type furnace, so which allows aluminum copper or aluminum silicon samples to solidify, or even if possible other materials possible, to make the directional solidification. And so here the sample have 2 heating zones, one hot zone and one cold zone, and it can move, so it's effectively making Bridgman setup. And then the samples solidified in ISS. So once the final sample may look like this. I'm not trying to give a science output of this setup, but from this MSL, what we learn. So actually, I have to say things went well. So it's like lot of cartridges on different materials are processed, and a lot of publications came through these experiments and associated publications. Of course, that's a good part of science. But at the same time, scientists understood some drawbacks on this existing facility. So particularly one of the key part is, when you solidify the sample, it produces some pores. So these pores actually, it's essentially reduce our ability to get the required results. And also one of the extremely bad part was, the pores are thermophysically different situation. So that will really bad impact into the solidification. So actually, it includes some volume compensation device on these materials, but its scientist's idea was sometimes this volume compensation device did not work as expected. And also, it completely designed has some limitations. Even though it's looked like Bridgman furnace, its crucible was made out of boron nitride. It's not provide some conductiveness, provide not ideal Bridgman conditions. And also, so in-orbit processing, delays in orbit processing was really delayed, so it was not well enough with the time with researchers, recruitments and other things. And also, we experience a long lead times to upload and processing and download. And basically, we identified improvements and solution for this type of conditions, extension of technical capabilities, cooling rates beyond some kelvins per minute, that means much faster cooling rates, and also that means quenching, to make the quenching better, so that means we can preserve the solidification conditions. And also, this type of a program need to be ideally going together with thermal modeling of the furnace setup, so that will allow to better analyze whole experimental scientific output much efficient way. So of course, we have some models, but they may not dedicatedly develop for analyzing these type of experiments. So then I go to the electromagnetic levitator. So again, Florian and another colleague detailed this facility. So I just try to, its basic objective was containerless processing of metallic and semiconductor materials for thermophysical property measurements and solidification studies. So it can provide the basic data measurements for viscosity into some insights into welding processes. So it's again, significantly things went right. So 3 batches of 18 samples and different materials were processed. So a lot of publications from these thermophysical measurements. So information exchange and collaboration with groups went well, and high yield of experimental cycles in operation. However, there are occasional loss of science due to variety of issues like sample getting stressed, cross-contamination between oxidation and oxidation of samples. So for example, I remember one of the presentation this morning explained that how the previous residues from other experiments affected to the next sample and its surface activities. And also, non-replaceable lifetime limiting components like coil systems and mirrors did not help to get the best outcome. And when we consider these things, we identified extension of technical capabilities, particularly enhance sample visibility at low temperatures, and basically with infrared cameras and other high temperature measurement system need to be integrated, and also the cameras through multiple axes can yield much better insights, scientific insights. That's something we identified with current EML setups. So, and then I go to the transparent apparatus, transparent alloys apparatus. Again here, it's basically Bridgman type furnace setup, but to design with low temperature transparent alloys, and with cameras on multiple directions, side view and oblique view. This setup also tested across multiple platforms. And things are right, it's multiple experiments completed and a lot of publications. But we understood this long preparation time were involved, and limited communications with the industry also, somewhat negative aspects came. And also, sorry. And also one of the key part, it's data download time. So which we discussed that I identified, it's taking very long time to download this telemetric data into the scientific researchers. And also, what we understood from scientists is stability of the electronic and software systems can be made much better in this case. So then I can come to the XRF facility, X-ray facility. Here again, the complete details were given in this morning presentation. So it's basically what here we have a X-ray source and a X-ray detector and camera, and with again furnace. It could be directional or isothermal furnace, and we have thin metallic sample which solidifies here, and X-rays we can get the in situ X-ray imaging. These setups were tested in parabolic flights, sounding rockets, as well as it's supposed to fly in ISS in 3 years time, 2027. It's actually one of the key important parties. Here we can take directly X-ray imaging of solidifying metals, dendrite solidification. And also, the sample is intact, and we can take down the sample into the earth, and we can compare with ground ex situ experiments. So we have again here there are we get the publications and it's good scientific results provided, but we found it's in this program this instead systematic approach. We going from experiment to experiment. So sometimes. And also sometimes due to sounding rocket experiment, it's due to the data loss, so broken parts during landing. It's due to hard landing, and some cases gas bubbles provided. Again, porosity provided valuable data from the samples, getting valuable data. And again, here we found some opportunities that if we can have better temperature characterization and advanced modeling can help a lot to define science and make the analysis better and extract the better science. And also, for the what we call here porosity problems, if we can make the much better sample, if we can identify the better sample preparation process, it might help to get the 100% out of the experimental opportunities. Okay, so that's what we had for the moment and what we identified. What went well, what went wrong, and what are the opportunities. So here, if you think about post-ISS material science research in low Earth orbits. So actually, we do not know exactly what are the facilities going to come. So here I'm trying to show what we have now. It could be this type of commercial facility or something like Space Rider or something, which we came to know about what's ESA having or trying right now. But we tried to, as a facility definition team, we did not try to stick into one facility or something. We just tried to develop the general concept, what we try to want. And basically our work is based on the material science white paper is a white paper, material science. We can particularly identify in the material science white paper 3 basic areas: thermophysical properties, structural evaluation, and space exploration. And we have some subtopics. So particularly what we have identified is our basic concern in material science or solidification science. So our basic scientific questions are always based on thermophysical properties and structural evolution. And also we need to understand things, these thermophysical properties and structural evaluation across different materials. And particularly when you see alloy systems. And also, this should be is multi-user facilities, and it should allow to use any facility which you are going to have a multiple type of samples, and sample batches should be able to do with multiple iterations. And also, when we go into, when we review the previous work and existing requirement, and also in the light of material science white paper, we try to focus on 3 areas we have identified. First is containerless solidification, and then the solidification, that I'd say ideally directional solidification, and also the new area we recognize is additive manufacturing. So this is more to the applied materials research area. So actually these 3 areas, there are 2 types of measurements we expected to focus on. So first, we would like to have in situ characterization capabilities as much as possible on each of these area. At the same time, we would like to have samples downloaded to Earth and to make the comprehensive program to make these samples analyze on Earth ex situ analysis in detail appropriately. So if I go into post-IS 3 areas, when we go to first container solidification, so it should be a purpose basically on it's gravity-related scientific issues on thermophysical properties and structural evolution. So to address this is the main purpose. And it's we don't say it's reasonably different from current scientific requirement. But our main thing we see is we can extremely improve diagnostics and communication abilities in any future facility. So still these are still being discussed, but we can understand we can increase the temperature, accuracy, and resolution and measurements, and also how we can improve the. So we need, in fact, that we need improved imaging and also improved temporal resolution. But here still these need to be decided and still need to be on discussion. And also we particularly identified in this case the communications need to be extremely essential to improve. So and also we identify some possibilities related to this one. It includes the possibility to study lower melting point and volatile materials as well as high melting point alloys. So that means increasing the temperature range on both sides to study. And also with multiple cameras, we realize that it's possible to get a more 3D picture of the sample in situ, 3D idea about the samples. And also by making streamline and also with streamlining with the analyzing capability. So the we suggest, or any facility should be have a higher overall science throughput with making all the process more streamlining. So then the second area we are focusing on, or we identified, is directional solidification facility. So that's again it's combining with, or I would say it's a kind of complementary to existing X-ray facility as well as directional solidification facility. So it's here again. It's to purpose is addressing the gravity-related scientific issues on structural evaluation. But here we particularly focus on improving temperature accuracy, temporal resolution, and spatial resolution of our measurements. And also we expect to improve our communication, telemetry data during sample processing, and real-time commanding for processing parameters. And again, we expect to increase the temperature range. That means high temperature alloys can be able to study using this facility. And if I go to our third area, which is the newer area, is based on additive manufacturing. So here to focus on addressing gravity-related scientific issues on in-space manufacturing. So this basically we are expecting to, or we are recommending development of self-standing research facility based on concept from ground research. So that means to test some test bed to test additive manufacturing ability in microgravity conditions. So this should be again modular type, sorry.
Maybe there was an animation or movie? Or?
No. Okay, can you go to the last slide? It's only one. Yes, so I'm just short of this slide. So based on this, our basic recommendation, okay, tentative, still we are trying to finish. It's so we are looking at the development of next generation containless solidification facility and directional solidification facility and additive manufacturing facility to post ISS LEO platform. And also we recommend that the seamless transition from current facilities to the post ISS era facilities. And also one of the key point, even though not the facility, so we would like to recommend that create and safeguard the necessary preconditions for science community. So because it's sometimes these facilities come without scientist time. So it would be really helpful to get the best output if you have more streamlined scientist time also we can get with the facilities. And also, finally, we should have a strategy for use the ground facilities to do better ex situ post-mortem analysis.
Thank you very much.
Okay, thank you.
Thank you for this presentation. Do you have any question also on the audience? Otherwise, maybe I will ask you a very quick question also, just because of time. In material science, if you look at the material science lab, EML, most of those facilities have been built, and then there was announcement of opportunity. In the future, is it something that this is the same process you have in mind, or did you look at when do you ask for, let's say, proposal, research proposal?
Okay, so to be honest, I don't have a direct answer. So because we are not, we know that it's beyond 2030, but implementation level, we have no idea. I think it's basically
Let me formulate. Before we start to build this type of instrument, do we need input from the scientists, or this is a top-down approach, and then we decide to have a certain facility, and when we have it, when we have the specification, we open for utilization?
Okay, I think it should be my personal opinion.
Yeah,
As a
sure.
scientist, I would like if we can have the engineers can have scientist idea and involvement, and particularly in material science, I would say somewhat we are the community is anyway sitting in between science and as well as engineering. So they are somewhat really capable of coming into the equipment, and what I see in even previous cases, the scientist has involvement on building things.
Thank you very much. Any other questions on the floor? I know that it is normally late, but if we have maybe just a very quick one in terms of diagnostic. For example, you explained that experiment like a material science lab is done fantastic. Also, at least in general, a lot of publication. And but you say, for example, you are more looking for institute diagnostic. This is something that you want to advance. And currently, I know that ESA is developing X-ray facility. Is it something you have in mind, other type of diagnostic? Or?
Okay, so we are still in discussion about what exactly. But if you take, again, I'm coming here to, I can give you my personal opinion. So, you see, if you can think about XRF, the same one, with some different thickness, different modular approach. So now our X-rays are getting better. So at least we can have the solid liquid interface to try to find where it is while during. So it's a kind of the hybrid, something the modular hybrid between our MSL facility as well as XRF. So which can fix to the both worlds, but it should be in a modular approach anyway.
Thank you very much indeed. So maybe I will review our time. Perhaps we have to thank you again. And,
thank you.
Thank you very much. And just a final announcement also. Please remember that at least on the same topic, we have a facility definition team also in fundamental physics. And that's the very similar approach. The presentation will be on the last day in the plenary sessions. So it will be in the room downstairs. And also, I would like to take the opportunity to thank all the speakers and all the scientists that were involved. I think this is super valuable in exercise for the agency. And so thanks again. Thanks definitely for that. And I would like to thank also my colleagues that are already escaped here. But I see Wim, Marco, and Pepe also that did a lot of coordination for this exercise. The idea also after that is that those reports will be public. I don't know exactly when it will be released, but and it will be shared, of course, with all the ESA partners that are involved in our program. So this is definitely something that will be used for the next ministerial conference. Thank you very much. Bye.